Hello everyone, welcome back to Calculus 2. In this video, we are going to talk about Chapter 1, 1.1, Approximating Areas. So just I want to give you guys a brief idea what we're going to do in Chapter 1.1. So if you remember, just quick thing, everybody knows how to find out the area of the right triangle. If you have the bottom length and if you have the height, so let's say this is A and B, A times B divided by 2. So that's how you're going to find out the area of the right triangle. Or if you have a shape of circle, pi r square, so pi times the radius square gives you the area of the circle. But now let's say we have a very ugly shape. Let's say if I have the shape something like this. So I have a function. And I want you guys to find out the area of this shaded part. Can we find out that? So we don't know, this is not really square. This is not the rectangular. This is not really the shape, the geometric shape that we know. So this is the main idea. How would you be able to find out the area of an irregular region bounded by the function? Okay, so 1.1, they're going to help us to find out how to find the area on irregular region. Okay, so that, by using the summation notation, we will be able to find out the area under this curve. Does it make sense? So this is not just a simple like calculation from the trigonometry or calculation. We are actually going to find out the area, which is an unknown shape. Okay, so I will show you how to do that. So the first thing we should know the concept of the summation notation. So some of you guys maybe heard about this from the pre-calculus, the summation notation. So let's just quickly recall the summation notation to calculate sums and powers of integer. And I will show you how this tool gonna help us to find out the area of the irregular region, okay? So let's talk about the sigma notation, okay, or sum notation. Typically, the sum notation is presented in the form, so let me write it as a red color. Summation, this is the summation note, and you have the general form of the list of the number. So let's say that is AI. And then I1 up to n. So many people confuse what does it mean I1? This is the beginning number. Okay. And then n is your ending number. So what does it mean? Summation from I equal to 1 to n and AI. So this summation notation indicate that you are adding from, so the I is the index. You can change it from 1, 2, 3, 4, 5 up to n. So A1, that's your first number. A2, you're keep adding the next number up to an. Because my beginning number was 1, my ending number was n, so that you're keep adding all the list of the number AI from 1 to n. That's how we're imply what the summation notation shows you. So one more time, where AI describes the terms that you're actually adding to, and then I is the index, because the index means you're changing the number. So the bottom is a beginning and is ending number. So this part can be any format. So as I see, if I have I, what does it mean? Your beginning number is 1, so you're keep adding the next number 2, 3 up to n. So many people do not want to write down all this the list of the numbers. So by condensing it, the summation help us to condense that information, the same information. So as I show you, this is an. Actually, this one should be AI. So that I'm going to change this, because you are plugging in the number into I. So A1, A2, up to AN. So all this long information, you can condense it by using the summation notation. Does it make sense? So we got the concept of summation notation. It helps us to find out all the summation of the long information. So let's take a look at the following question. So I have the list of the number. Well, like 1 plus 2 plus 3, we know what's happening, but I just want to condense it by using the summation notation. So therefore, we can check what happened. 1 is the beginning number, 20 is the ending number in this information. So just use a summation notation. I equal to 1, that's your beginning, and you are stopped at 20. And then what is your the term that you're actually adding to? It's going to be 1, 2, 3, 4. So you keep adding the next simple number. In this time, I, right? So I is going to be 1, I is going to be 2, I is going to be 3. So you're stopping at 20. So you can condense this long information into this summation notation form, okay? So likewise, we can also do the backward. Now I already gave you the sigma notation. This is a sigma notation. So what does it mean in this sigma notation? The beginning number is a 2, ending number is 7. So you have a term, SI, that's the term that you're actually adding. So the first one is a 2, the beginning number, and then you're actually stopped where? 7. So that's going to be your long information. This is the short version with the condensed form. This is actually you're adding to. All right, so you are getting close to the concept. The summation notation is not really difficult thing. You can actually think about it. So let's look at one more example. Write in sigma notation and evaluate the sum of term 3 to the I, and then they gave us I is going to be only 1, 2, 3, 4, 5. So check it out. This is my term that actually I'm going to add. 1, gotcha. This is a beginning number. 5 is the ending number. So we can say, we can condense it. Summation I equal to 1. You stop at 5 and 3i. That's it. And then they actually want you to evaluate the total summation. So we know that means 3 to the 1, 3 to the second, 3 to the third, 3 to the fourth, and you stop 5. We literally evaluate the each term, 3 to the 1, 3, 9, 27, 81, 243. So if you're adding them, the answer is going to be 363. So you can list all the information by looking at the summation notation, or you could do the backward. You can condense all the long information in the summation notation form, or you can actually evaluate it. So that this is how we are applying the summation notation. Okay, so this is a simple concept. And now what I'm going to do in the next slide, I'm going to show you a couple properties of sigma notation. Okay, there are some patterns. So let's go to the next slide slowly and surely. All right, let me go down, down, down. So I'm going to introduce a couple, 6 properties. So number 1, number 2, number 3. These are really popular properties. And then you will see why very soon. 4, 5, 6. So let's look at the first one. So when you look at the first one, we know that the beginning number is 1, ending number is n, and the pattern is I. You keep adding the next number. So let's say here, if I list the information, it means 1 plus, 2 plus, 3 plus, 4 plus, you keep adding up to n, correct? So now let me ask you, hey, can you find out the beginning number 1, ending number is 100, and then same pattern. Can you find out what would be? So Professor Ben, I know what that means. The beginning number is 1. The next one is a 3, and then the ending number is 100. Am I really adding all this number? I know it takes a long time, right? I know you can get it. You can find out the answer if you really spend time in calculating 1 plus 2 plus 3 plus 4 plus 5 plus up to 10. but I feel that it's a time consuming, right? So what happened is whenever you have this pattern, 1 plus 3 plus, you keep adding the next number, just use this formula. N plus 1 divided by 2. So what that means is the ending number times ending number plus 1 divided by 2. So what I'm going to do, in this question, we already know the ending number is 100. So 100, I'm just looking at this formula, 100 and adding one more, 101 and divided by 2. So if you simplify, it's going to be 50. And then what is 50 times 105? It is going to be 5050. So that's the total summation from 1 to 100. And it's a pretty shortcut. Well, you can adding all the number, but it takes a time. You can use a calculator though, but it still takes a time. So what I'm saying is this formula help us to find out the same answer in a short time. So just, if you have this pattern, the summation is going to be simply passing through this formula. Again, one more example. I'm going to make a little bit space. So here, let's say I want you guys to find out summation, the beginning number is 1, you stop at 50. And the pattern is 1. Pattern is I. We already know what that means. 1 plus 3 plus whatever, you stop at 50. You can calculate it by hand, but takes a time. So what are we going to do? Ending number and then adding 1 divided by 2. So 25 times 51. 25 times 51, 1275. That's the summation from 1 to 50. So that's why this is a more efficient way to find out the total summation. This is number 1 property. If you see that pattern, just use that formula instead of using all the handwriting calculator. Does it make sense? So likewise, I'm going to show you a couple more. So how about the second one? Ooh, looks a little bit fancy. So the different thing between number 1 and 2, the beginning number 1, ending number is n, but the term is I to the second. So what does it mean? So actually, I'm going to make a little bit of space here. So I'm going to bring here number 2. So number 2, we have a beginning is 1, ending number is n. So I to the second means what? 1 to the square, 2 to the second power, 3 to the second power. You're keep adding, second power up to n to the second power. Well, it's gonna be double time, right? Because it's a double number. So same thing, if I'm looking for 100, the beginning number 1 and I to the second, we know what that means. 1 square, 2, 3 second, 100. Are you really gonna calculate it like by hand? No. So according to this formula, the ending number times n plus 1 times the 2n plus 1 divided by 6 gives you the direct answer shortly. So therefore, we have ending number 100. Ending number plus 1 is 101. And then 2 times 100 is a 200 plus 1 is a 201 divided by 6. So if you do this work, this is much easier, isn't it? So let me simplify. So I do have 100 times 101 times 201 divided by 6. I got 3 3s 8, 350. So this is a summation from 1 square, 2 square, 3 square, up to 100 square. So just use this formula if you have I to the second. So that's a different. So one more pattern. What if I have I to the cube? So this is I to the cube. And then this is the formula that you're going to actually use it. So one more thing. This is number 3. That means I to the third, 1 to the third, 2 to the third, you're multiplying same thing 3 times, right? That takes a triple times. So if I have 100, or I'm going to make a little number, 50, I equal to 1, I to the third. So what does it mean? I to the third, 2 to the third, 50 to the third. So what happened? You don't need to calculate by hand. Just look at this formula, ending number in this time 50. 50 to the second, and 50 plus 1 is a 51 to the second over 4. So if you calculate that, 50 times a 50 is a 2500. So let me write it, 2500. 51 times a 51, 2601, and you multiply that and divide it by 4. So let me calculate one more time. Divided by 4, you should get 1,625,625. It's a big number. That's why this formula will be more efficient. Does it make sense to you? I hope so. So check it out. This is a summation notation property. If you have the term simple I to the second or I to the cube, just utilize this mini formula. Okay. All right. So we got the concept. Let's take a look at other properties. So just quick property. These are pretty simple. So if you have a constant, right? So if you think about number 4, so this is number 2. This is number 3. That was number 1. So number 4 property means, what do you guys think? You have constant. So n, I equal to 1, beginning number 1, ending number n. Let's say you don't have like any index here. You have a constant. So what that means is you are adding 3, 3, 3, 3, 3, 3 n times, right? So this is number 1, second, third, nth number. So simply 3 times n will be the answer. So that's what I'm saying here. If you have a constant, multiply with the ending number. Okay. Same thing, if you have a constant, you can bring it to the front. So maybe you heard about this one in the calculus one. Constant, you can bring in front of the limit, bring in front of the differentiation. You can bring it to the summation notation as well. So you can think about that. And we can also use a distributive property. So you can adding them together or you can separate them together. So it's going to be the same answer. The last one, you can have a different, lengths. So I can add, let's say we have 1 to the 100. You can have a summation I equal to 1 to 50. So that's the summation from here. And then if you want to go to the next one, 51, right? So the next number will be 51. I equal to 51 and you're ending at 100. So that's the second part. So it's the same as from I equal to 100. So that's why you can separate the lengths because the total length is the same as a small length as well. So 1 to the 5th, same as plus 51 to the 100. That's going to be same total 1 to the 100. Okay, so that's all the property that I wanted to show you here. So number 1, 2, 3, 4, 5, 6, you will see the benefit of using in many different questions. So just keep in mind. Let's look at the following example 4 and 5. So I'm going to change that. So write using sigma notation and evaluate it. The sum term is going to be this. So we know this is beginning, ending. So what happened? So it means I equal to 1. They stop at 200. We have I minus 3 to the second. Are you guys following? So what does it mean? Actually, this means you have to think about, simple way, not like a complicated way, but I'm going to actually go to this question. I'm going to write this question, copy. I'm going to put it here because I need more space. So I'm going to bring it here and I'm going to actually minimize it a little bit. And then let's do the number 4. So number 4 here. So number 4, I'm going to copy that. We are looking at this question. So I'm trying to find out what the summation from 1 to 200, and that's the pattern. So we know it is going to be 1 minus 3 to the second, 2 minus 3 to the second, 3 minus 3 to the second, up to 200 minus 3 to the second. As you see, this is too much work. So I'm trying to just simplify the given term. So you know what? Let's simplify that. It means beginning is 1. I'm going to actually expand I minus 3 to the second power, means you're multiplying I minus 3 twice. So let's expand it. So it's going to be distributive property I to the second, and then it is going to be 6I plus 9 if you expand it. So what does it mean? According to the property, I can separate them. So it means 200 I equal to 1, I to the second, and then 200 I to the 1, 6I plus 200 I equal to 1, 9. Are you following? So I already see the pattern. I see the second. So we're going to use the formula. Go up, 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 up. This one. So this formula going to help us to simplify the total number of that. And then I can bring 6 to the front. So if you do that, it is going to be minus 6, 200 I. And then what do you guys think? This is another formula, right? I and n plus 1 over 2, right? We're going to use the mini formula, and this is the constant. So we know that this is going to be 200 just times n. So let's wrap it up. So what happened? The ending number is a 200, 201. 200 times 2 is a 400, 41 over 2. So this is the first term. And then second term, 6 in front. And I have a 200, 201 divided by 2. This is the second term. Are you guys okay? And plus 1800. So I'm going to simplify as much as I can. So what I got, this is going to be 100. This is going to be 3. So that you can actually now calculate it. So we're going to get 100 times 201 times 401. So this is going to be 8060, 100 minus 300. So the next number, 3 times 200 times 201. So you minus 120, 600, and adding 800. So if you calculate it, let me calculate for you, or you could try minus and then adding 1800. So the answer should be 7,941,300. That's the answer. So you see that it's a big number. If you're trying to find out this answer by hand, you might have high possibility to make a mistake. So don't do that. If you see the I second power, use this formula. And then if you see the I, use that formula, and then constant times the ending number. So I'm literally using the property. Are we okay? So that's what it is. Check it out. Okay. So we got that answer. Oh, I think I have a little mistake. So let me go up, 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 up. In the formula, actually, they say divided by 6. You see that? I divided by 2. So let me change this. Actually, instead of 2, it should be 6. Sorry. So let me recalculate it. So we cannot divide by it. So now let me just recalculate only this part. So 200 times 201 times 401 divided by 6. Actually, we got 2685700. So if I recalculate it, so subtract and adding them, I got actually 2,567,900. So this is the better answer because I need to divide it by 6, not 2. So let's be careful. Okay, so that's what it is. We got this concept. Are you guys okay with that? Number 4. So I'm going to hold up. Maybe you can pause the video, check it out. Did you really understand this concept? If you got this one, you can restart that video. Let's go to the one more example. So I have a one more example. So actually we finished number 4. Let's go to number 5. So let's think about it. This is the term and the ending and this is the beginning and this is ending number. So let me write this information in terms of the sigma notation. So it'll be I equal to 1, ending 6, I to the third, I to the second. So let me bring this one to the bottom because that's something I want to do. Number 5. Paste. Okay, so what do you guys want to do here? Are you really going to use by hand? No problem. You could do it, but it takes a long time. I want you to actually simplify using the formula. So let's separate it. It means beginning, ending, I to the third, beginning, ending, I to the second. Uh-oh. I already see I to the third, I to the second. So there is a formula. What was the formula? Go up, right there in second. So in this time, let me write down the correct one. N to the second, n plus 1 to the second over 4. And I to the second, n plus 1, 2n plus 1 divided by 6. So we're going to use that formula, correct? So let's do it. The ending number is a 6. So it means 6 to the second, 6 plus 1 is a 7 to the second, you divide it by 4. Minus the ending number 6, 6 plus 1, 7. 6 times 2, 12, 13, because you're adding 1 and divided by 6. So if you calculate that, you will get the total summation. So I have, this is a 36. It's going to be 9. It's going to be 1. So you can simplify 9 times 49 minus 7 times 13. I got 350. So that's the total summation of this form. Okay, from 1 to 6. So we practice how to simplify the number. Although you have a long list of information, the summation notation and their property help us to find out the total summation. Now, this is the warming up, right? Because we have another goal. I'm trying to estimate the area of irregular shape, right? So that's something actually I'm going to move on. So if you got that one, actually, I'd love to see your guys' face or thumbs up. But anyway, I hope you guys doing fine. So let's talk about the real goal that we are having in 1.1. Here we go. So you got the concept, 1.1. So this is the goal in chapter 1.1. I want to find out the area of this ugly shape. I don't know, this is not the circle, this is not the right triangle, or this is not, square. This is something is irregular shape that I've never seen before, but my goal is to estimate this area. So what mathematician, thought long time ago in ancient time, they had a brilliant idea. They actually thought about this way. What if we are creating many rectangular under this area, correct? So I could have this rectangular. You see that? I'm just creating the rectangular. And then each rectangular has the same length. Okay, so we have equal length rectangular under this area. But the reason why I'm creating the rectangular, because I know how to find out the area of the rectangular, because simply the length times the height, that's going to be the first area. The second length times the height will be the second area. If you keep adding all this area of the rectangulars, you might be able to estimate the entire area, the blue area that we are looking for under the curve. It might not be perfect answer, but we can approximately estimate it. So here is the thing. The point is you need to find out the equal length, right? So the equal length, let's say we have A to B. A is the beginning number, B is the ending number. So you have here, actually I need to make a better line. So let's say this is A, this is the ending. A, I'm gonna say this is x0. And then the next one, x1, x2, x3, up to da. This is going to be same as xn. So I'm trying to find out the equal length. This length should be equal to the next one, next one, next one, next one. So how do I find out the equal length? We call that is partition. Equal length between A and B, we call that is a partition. So that's going to be B minus A. And I don't know how many rectangulars that I'm going to have. I'm going to divide it by n number. That's going to be triangle X. We call equal length. So highlight it. This is the equal length. So you're going to have here many same equal length. That's the partition. So now I'm trying to find out the area. So the first area, this is the length times the height. So let's say this is the x1, right? And this is the x2. You have a function f of x. The height is going to be, for the first rectangular, is f of x1. This is f of x2, f of x2, 3, 4, 5. So what happened is the area we are looking for, the area under the shape, the first height, you could start from here or here, doesn't matter, but I will show you the difference later. But let me just calculate from the first height, because that's x0. x0 times the equal length. So this one times that, plus the second rectangular, this one times that. So x1 times that, and you're gonna keep on going up to n, right? If you do this work, you might be able to estimate the area under the curve. It might not be perfect, but that's okay. So this is the height. This is the length of the first rectangular. This is the height times the length of the second rectangular. You're keep adding many rectangulars area, and then you're totally adding them. You can find out the area under the curve. That's what the ancient mathematician discovered. So what do you guys see? Keep adding. Oh, that sounds like a summation notation, don't you? So this one, you can condense it, summation, I equal to 1, right? Ending number n, fxi times the x length. So actually this, I'm going to show you more, but this is the idea where the summation notation is working to find out the area under the curve. So we call actually this one Riemann-sum. Okay, so I just want you guys to understand the concept, right? There gotta be a way to find out the area under the curve. The meaning is you're gonna find out many rectangulars with equal size of the length times the height, you know, to find out each rectangular's area, and summation. If you're adding them all, you're gonna find out the total area under the curve. Does it make sense? So that's the simple idea. And now I'm gonna make it more. I'm gonna make it more, analyze it. So let's take a look at the next slide. So here we go, more and more specifically. So we understood, okay? The simple way is you're adding the height times the length, of each rectangular. But now you have a two option. You might be focusing on the left side as a height. So this rectangular, I'm looking at the left side. I'm going to consider the left side of the rectangular as a height. And then for the second rectangular, still, I'm going to consider this one as a height. But when I look at the second image, this image, I focus on the right side when I calculate the area of the first area of the rectangular. This one, I'm focusing on the right side. So you have a two option, whether you're gonna use the left end point, left side, when you're measuring the area of each rectangular or right side. So you have two options. So they are actually giving you the different answer. Let's take a look at it. So if you focus on the left and the side point, okay? But the equal length does not change. The length is always equal. So this is the length. So height times the length, that's gonna be the area of each rectangular. And then what happened here? This is, we start from here, the beginning one. So if you have a long length, always AB, this is x0, this is xn, the next one x1, x2, xn minus 1. So this is a specific length order. A is x0 and B is xn. So therefore, what happened? The height is going to be, we have f of x, you're changing x0. So we start from x0. So x0 times the height, f of x1 times the height. And then the ending number, it's going to be right there, not the n, not the xn, the before you're gonna stop because we are focusing on the left side. So right there. And then what happened? I can also condense this information with the summation notation. So this is the height times length, height times length, height times length, adding all them. So the summation notation will be the beginning one, but the term is going to be xi minus 1 times the length. Because if you're plugging in 1, the beginning should be 0, so we have to xi minus 1. And then same idea, you could focus on the right side, right? So the right side is much simpler because we exactly start x1, x2, x3, and you're exactly ending xn because we're focusing on the right side. So this is going to be beginning x1, x2, you're exactly finishing at xn, and then summation notation will be I equal to 1 beginning, and you're exactly ending n, so you don't need to change actually. So this is the way, these are the ways to find out the area under the curve. So now you might be confused. Do they gonna be the same answer? So here we go. The actual area that we are looking for, as you see that if you're focusing on the left side, we do not cover this area. You see that? There's an arrow. So left end always underestimate the area, underestimate it. There's something we didn't count it. For the right side, as you see that, you overcounted. So this is overestimated. Therefore, the actual area is going to be between left-ended point area or left-ended height, because this is underestimated, and then right-ended height. So that you can estimate it approximately. Okay, so that's the concept. How estimate the area of irregular shape. There gotta be a way. We call this as Riemann sum, which means you are using the summation notation, adding all little rectangulars area under the curve. So one way, focusing on the left, or another way is focusing on the right-ended height. So far, I gave you guys a lot of concept, right? I'm gonna now do the real problem. I'm gonna just do 3 examples, actually 2 examples. So if you guys are okay, let's really do the work, okay? Here we go. So I'm gonna change the color. Let's go to the problem. So in this question, use both the left point and right end point to approximate the area under the curve. So we have the function. So if you draw that function, it is gonna be beautifully parabola shape. So this is fx equal to x to the second. I wanna find out the area. So they say on the interval, so 0 to on the x-axis. And then they say, find out the area under this curve. Am I correct? So this is not really right triangle because there's a curve. So we have to use the Riemann sum, which means you're going to create many rectangular. So step 1, we're going to use either left or right endpoints. So actually, we're going to do both. And then they want you to have a 4 rectangular. So here, if you are using endpoints, so we're going to begin here. 1, 2, 3. So if you look at this image, we have 0 and 2. Between 0 and 2, you're going to have 4 different terms. So what I'm meaning by that, step 1, n equal to 4 between 0, 2, equal length, which means the partition always b minus a over n. So we know the ending 2 minus 0 over 4, because we're going to have a 4 rectangular, 1 over 2, 0.5, isn't it? So every 0.5. So next one, adding 1, 1.5. So we have exactly 1, 2, 3, 4 length. So that's something happen here, correct? And then one is left end, another one is right end. So the left end, if you're focusing on here, underestimated. This is the area that we are looking for. So let me calculate it. We're gonna focus on the area on, with the left ended. So we're gonna start from here. The left F0 times 0.5, because equal length is 0.5. That's your partition. We found out 1 over 2, that's 0.5. Plus the next one is 0.5 right there. The left end we are focusing on. This is 0.5 times the equal length. Plus the next one is here 1. So this is 0, 0.5, 1, 1.5. Sorry, this is not 4, this is 2, right? So 1, 0.5 plus your stop at 1.5, because that's your 4 points. So 0, we're going to plugging into the equation. 0 squared, 0 times 5, 0.5 squared, 0.5. Height times length, height times length. So 1 square, 0.5, 1.5 square, 0.5. So if you're adding all the number, you should get 1.75. That's the area. This is the area when you're focusing on the left side. Are you okay with that? So I'm gonna minimize it for a second. Okay. All right, we good. And I'm gonna copy this because I need to find out the right side ended area. So the right side ended area, I'm gonna get rid of it. So we have this. So the right side ended area, what happened? We're gonna focus on the right side area. So let me just redraw. So here, 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 right side overestimated, correct? So the area focusing on the right side, you're gonna begin 0.5 because 1, 2, you have focusing on right side area, right side area, right side area. So 0.5. So F 0.5 times the length F1, 0.5, F1, 0.5, 0.5, F2, 0.5. You're exactly ending at 2. So therefore, 0.5 second power, because that's the height, that function given. And then 1 square, 0.5. 1.5 square, 0.5. Sorry, a little bit of calculation, but we got it. If you calculate that, you should get, I'm gonna just bring this number here. You should get 3.75. So as you see that, it's overestimated. So what is the final answer? We believe that the actual answer is going to be between 1.75 and 3.75. Okay, so that's going to be the range for the actual area. So this is how you're actually calculating, finding the area of irregular shape by using this summation notation. We call this is a limit sum. I hope this is clear to you. Okay, so I'm gonna do one last example. So let's take a look at one last example here. Maybe you need a type of time to copy that. All right, so here we go. Ooh, we have, okay, find out the area. So this is a given function. And then between 0 to pi over 2 and equal to 6. So we have a 6 rectangular step by step. So just, you know, let's try to draw that image. So the lower sum means that in this time, you're only focusing on left-ended height. So as you know, this is the sine function, up and down every 2 pi. So this is the pi, this is a 2 pi. Here is a pi over 2, so 0. So this is a sine function. The regular sine function, every 2 pi, you have the same patterns going on. But in this time, they're actually stopped at the beginning is a 0, ending is a pi over 2. So they want you to find out this area. Does it make sense? And then to find out the area, create 6 rectangulars. So I'm going to bring this image. I'm going to just make minimize it. So here, so if I draw, that's the pi over 2, and this is a 0. Okay, so we are looking for this area. So I just maximize it a little bit. So here, step 1, we need to find out the equal lengths. You're gonna have 1, 2, 3, 4, 5, 6. You have 6 rectangular because n is a 6, and they want you to have left-ended height. So we're gonna begin exactly left. So underestimated, underestimated rectangular area. So step 1, find the partition. B minus A over N. So B pi over 2 minus 0 over 6. So if you divide it by, what is it? Pi over 2 over 6. What does it mean? Pi over 2 divided by 6. Kentucky Chicken Fried, you know, keep the first fraction, change division to multiplication, so flip over. So pi over 2 divided by 6 means pi over 2 multiply 1 over 6. Pi over 12, this is the partition, the triangle X. Dun, 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 dun. So the equal length is a pi over 12. So I'm going to just look at this line. So here we begin 0. This is X is 0. Here ending pi over 2. This is X is, the X is 6 is the ending number. What would be the x1? X1 will be pi over 12. You keep adding pi over 12, pi over 12, pi over 12. So the next one, 2 pi over 12, x is 3, 3 pi. So this is a 3 pi over 12, x is 4. This is a 4 pi over 12. X is 5, exactly 5 over 12, x is 6, 6 pi over 12, you can simplify pi over 2, exactly same. So these are your number, right? We have a 6, points. So now we're gonna use the left-handed area. So we're gonna start from here, x is 0, you're ending x 5, because you're focusing on the left, 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 left to left, left. Height. So finally, the area f what? X is 0, and then pi over 12 is the equal length plus x1 pi over 12, x2 pi over 12, x3 pi over 12, x4 pi over 12. I just need one more. So here, f of x5, we stop there, pi over 12, because we are using left-handed. So what is f of x0? That's a 0. right? So we have a 0. So this is fx0 is a 0. Pi over 12. Fx1, we have f of pi over 12. I'm just changing everything. So f of 2 pi over 12, pi over 12, f of 3 pi over 12, pi over 12. Just hang in there. We have f of 4 pi over 12, pi over 12. Always I need couple space. So if I do the last one, f of 5 pi over 12, pi over 12. All right, so that's the number. And then this is the function fx equal to sine x. So you're gonna plugging in 0 pi over 12, 2 pi over 12 into the sine function. That's what it is. So sine 0 times pi over 12, sine pi over 12, pi over 12, sine 2 pi 12. You can simplify. This is a 6. This is a 1 over 6 pi, right? So this is a pi over 6. This is a pi over 4, pi over 3, 5 pi over 12. You can simplify. So this is a pi over 6 times a pi over 12. Sine pi over 4 times a pi over 12. Sine pi over 3, pi over 12. Okay, I need more space. Sine pi 5 pi over 12 times a pi over 12. So if you're watching this video, this is not really complicated. And the last one, sine. I knew that I just need more space. So I'm gonna actually simplify. Okay, so here, last one, sine pi over 2, that's a 6 pi over 12, pi over 12. Okay, so this is something you need to calculate it, but you don't worry about it. Go to decimal. So if you go to decimal, I'm gonna show you. That's a decimal calculator. So you're gonna literally plugging in all the equation. So sine 0, right? And you multiply pi over 12, and you are going to adding the next one. Just write all the term that we have. So actually I calculate that. Oh, so for you. So if you calculate with decimal, about 0.863. So that's the area underestimated because we focus on the left side area. So I show you two very important example. There gotta be a way. There is a way to find out the area under the curve. Okay, so that's the 1.1. We finished 1.1, and I'm gonna wrap up 1.1. So we talked about the Riemann sum. This is the Riemann sum. You are actually adding, all the rectangulars area. So that's the height, right? And then this is the equal length, the partition. You're adding all the rectangulars area. That's the summation notation, correct? And then we don't know how many rectangulars you're gonna have. So if you have a 4, we have a 4 rectangular. Let's say we have 8 rectangular, but the more you have, if n is infinity, if you have infinite number of the rectangular, that means you have less arrow. So we used to have a large arrow with the small number of the rectangular, but if you increase the rectangular, the number of the rectangulars, your arrow is going to be smaller. So this one is the central limit theorem. If you're learning statistics, so as, I'm going to write it here, very important, as the number of the rectangular, as n increases, we find less arrow. Therefore, there is a limit. You don't know how many rectangulars you need, but the large is better. So we're gonna increase the number of the rectangular up to infinity. So that's a limit concept. So this is the full version of the Riemann sum. Does it make sense? So this is the formula, but nobody gonna memorize it. So what happened is, later, this is the ancient time math. This is a long ancient mathematician discovered, Riemann sum. And later in modern math, we are changing this limit and summation as an integral. This is the integral symbol. And then you keep the height times the length as a dx and height. So this is the definite integral we're going to use in calculus 2. So this is the modern way to find out the same answer. So we are using the integral technique, and 1.1 exactly introduced the concept of the Riemann sum with the summation notation. And then we are going to use this idea with the integral concept. So I'm going to keep going. In the next video, we're going to talk about the 1.2. So welcome to integral. That's a calculus 2. So 1.1 was the introduction. The Riemann sum, actually the guy who developed this idea, the name is Riemann. So he actually had a brilliant idea. As you see that, keep adding all the rectangulars area, you are able to find out the area under the curve. So that this is the simple, all the classical way. Height times length, all the summation of the rectangular, and reduce the error by having many rectangulars. And later we are developing this one into the integral concept. So it's the same meaning though, but in calculus 2, you will see this format more and more. Okay, so that's all about it, 1.1. And I just want you guys to briefly emphasize one more time. This is the first 2 weeks, so please read syllabus and be aware what is our expectation. And definitely I do update weekly recording videos and lecture notes. So that's going to be your study resources. And if you go to quiz 1.1, so whenever we finish unit 1.1, each unit, you are supposed to complete the following quiz assignment. There are also embedded video you can watch. So I have a lot of resources for you so that you can have a efficient study skills. Make sure there's a meet and greet discussion, and feel free to participate in discussion chapter 1. So you have a participation point. So participating in the discussion board is important. So whenever you have questions, help each other. That's where you're engaging with other people. And that's going to be really great for the rest of the semester. Okay. So feel free to email me if you have any question, and I will see you guys during the week optional meeting. So if you have any questions, stop by there too. Thank you, everyone. I will see you in the next video. Bye-bye.